So hi devs, in this video I'm going to continue my discussion of the technical interview, and this time I'm talking about complexity analysis. Now complexity analysis can be a very complex topic, but for most junior level interviews it really can be simplified and I think that I can show you what you need to know about complexity analysis that you can get through your interviews without too much trouble. Now I have some notes just to make sure I don't miss and forget anything. So first of all, the thing to think about complexity analysis is how we talk about it and the notations that we use. We use what's called big O notation, and it's just capital O stands for order of, and we say O of, and then we put the complexity inside of it, of the parentheses. So this N refers to the number of elements in your data set. So this will be order of n, order of n squared, order of log n, so logarithmic. Again, I'll go through these in a little bit sooner. And then constant, we put a 1 in there, so it's constant. So linear, quadratic, these are the ones that you'll see the most often. And if you know and can kind of understand these, then you'll do fine. Logarithmic and constant. There's also a combination of these two that you might see a lot. These two, order n log n. And I'll explain why that's commonly used. All right, and this one, interestingly enough, is called typically n log n. Okay, so here are the runtime complexities that we're going to encounter the most often. And I would like to demonstrate the difference between them and how that fits into complexity analysis. So the easiest way to do that is to draw a graph of them, and on the x-axis we'll put n, which is the number of elements in the data set, and on the vertical axis we'll put time, which is the runtime, how long it takes to run. So let's start with constant. Constant means that no matter how big n gets, the runtime stays the same. So it's just a straight line. You can have, just a few elements or a huge number of elements, the runtime's always going to be the same. So they're really, really nice. You can do, if you can find a constant time algorithm for large numbers. Linear, let's talk about linear. Linear just means that as n grows, then the time grows in this directly proportional to it. So you can draw a line like that, this linear straight line. Not very straight, but good, you get the idea. So here's order 1. Here's order n, so it just grows linearly with it. Let's look now at quadratic. Quadratic, it grows like n squared. If you remember your math, this is a parabola, so it might look like this. Okay, and then finally let's do logarithmic. Logarithms, if you remember your logarithms, so we can have a number like 100. The log of 100 will be 2, it's the number of zeros, or the exponent. The log of a million is just 6. So the n can grow very large, very, very large, but the logarithm grows very, very slow. So it's really a great compromise between constant time and linear. So logarithms will grow just a little bit faster than the linear, maybe something like this. Okay, so those are the basic ones. N log n is just going to be the multiplication of these two, so it'll just be a line that just kind of goes a little bit above the n. All right, so with this graph you can actually see why we worry about complexity. We only worry about complexity as n gets very, very large. You see down here in small n's, it's kind of random and it's really hard to tell which one's going to be faster and better. So complexity really only matters if you're talking about very, very large data sets. Thousands, millions, tens of millions, billions of numbers. It starts to matter. But you can see in those cases it makes a huge difference because your n squared graph grows very, very fast compared to these other ones. So if you have an n squared algorithm for large numbers of data, you're going to want to work hard to get it down to linear or ideally down to the logarithmic. Okay? Okay, so I hope this gives you kind of the basic idea of what complexity analysis is all about. You've got your linear, quadratic, and all these growth times, and they really only matter as n gets very, very large. And the way computers are going nowadays, n has to get very large before this starts to make a bit of a difference. Interestingly enough, a lot of this complexity analysis you don't really encounter a lot in computer software, but they make a big difference in interviews. So they're good to know. All right, so let's get back to that question then. Knowing a little bit about these complexities, how do I decide which one my algorithm is? And I'm going to talk about that for a second. All right, so the trick to figuring out how the complexity of most algorithms is I look at the code and I find all the loops. Not all the loops, the places where you loop over data. So usually you will see something that is like a for loop for, let's see, I'll write this in JavaScript, let I equal 0, I less than n, where n is the amount of data, I plus plus, and so on. And you'll see that something like this. Now there are lots of different ways these loops can happen. It could be a for each, it can be a while loop in a lot of ways. So sometimes you have to look carefully to find them. Sometimes they'll be hidden in the libraries and library code, so you kind of have to know how some of those things work. But the idea is to just figure out in your algorithm that you're analyzing, how are you looping over the data. All right, so constant time complexity, there won't be any loops. Okay, that one's easy. So you look for loops, you don't find any, you think about how it is you're going to do this, and there just aren't any. Linear, there will be one loop that's like this. You just have this one loop here. So what this means is that I am going to be looping, and I'm going to be looking at every single one of the elements in my data set once. And so I touch every single one of them, so that's linear. And it's kind of clear because if I am looping over 100 elements, and it takes 3 seconds, then if I loop over 200 and it takes 6 seconds, then it's linear. As the n grows, this grows the same with it. So, what about quadratic? I'm running out of board space. So quadratic, what happens to give you quadratic is when you loop over something, you may end up looping over again, and usually you'll see that as nested loops. So you might see inside of here, and so on. So this is a nested loop. So what this is saying is that for every element in the data set, I have to go and loop over everything else. And so I'm doing it n times, and then for every one of those I'm doing it n more times. So I'm doing n times n, and that's quadratic, n times n. And these are nested loops. So if you see nested loops, then you've got a quadratic, or worse, depending on how many times you loop. Okay. The next one we're going to talk about is logarithmic complexity. This one's a little harder. It's a little harder to understand, and it's also a little bit harder to identify in the code. Usually it involves recursion. So if you see recursion, then you might want to suspect logarithmic. So the best way actually to think about logarithmic complexity is not by examining the code, but by thinking about what's happening. Usually in a logarithmic algorithm, you will examine some spot of data and you will throw away half of the data at each step. So for example, if I have a binary tree, and I'm walking down the tree, you'll notice if I start here and then I make a decision to move to there, then I've eliminated half of the tree from consideration. And then as I make the next step to there, then I've eliminated half of that tree. So at each step of the way, I'm eliminating half of the data. Another way to think about this is if you're doing a binary search. So if you have in a list your numbers in sorted order, and I can start in the middle. I jump to the middle and I say, okay, I know that what I'm looking for is smaller than that, so I'm eliminating this half of the list from consideration. Then I jump halfway between that and I end up here. I've eliminated this half of the remaining list. So each time I'm cutting the number of elements in half, and that leads to this logarithmic complexity. All right, so those are really the main things. You've got these four: logarithmic, constant, linear, and quadratic. If you can get those and kind of think through your algorithm and see how it's happening there, as you get better with this, you'll be able to do it without actually looking at the code. You'll be able to just kind of think through, this is what my code is doing. Oh, I'm walking through every single one of the elements, and you'll be able to easily identify which one of these it is. And that will get you good enough to get the complexity down for most interview situations. All right, so that's it for complexity analysis. You might want to watch this video a couple of times just to kind of get the concepts down. I went through kind of quickly, but that's the beauty of videos. You can watch them again and again, and you can kind of get through it there. And if you have questions, be sure and post them, and I'll see what I can do to help out. All right. With that, go off and do your complexity analysis and pass those interviews.